75%. That is the certified cut in energy cost from a new type of glass. Tested and verified in a Shanghai lab in early 2025. Glass that generates its own electricity while you look straight through it. Let me tell you what that actually means in plain English. A building covered in this glass stops being a pure energy consumer and starts becoming, in part, its own power source. You heard that right. The windows themselves, generating real, measurable electricity. And that is just the beginning. That number alone rewrites what an entire industry believed about transparent solar technology. But the part that changes everything is not the glass itself. It is how they solved a problem that had stumped researchers for 20 years. Hit a quick like and subscribe so you do not miss the next one, because by the end of this video you will understand exactly how ordinary glass became an energy source. For decades, the consensus in the solar industry was simple: glass and electricity generation did not mix. The National Renewable Energy Laboratory in the United States spent years testing early transparent photovoltaic concepts, and the numbers were never close to viable. The best fully see-through panels topped out around 1% efficiency. 1%. Compare that to a standard rooftop solar panel, which converts roughly 20% of the sunlight that hits it into usable power, and the gap starts to look less like a technical hurdle and more like a wall. Here is the problem with trying to make glass generate power. Sunlight carries energy across a whole spectrum of wavelengths, and the only way a traditional solar cell captures that energy is by absorbing light, which means blocking it. But a window has exactly one job: let light through. Ask a material to be transparent and energy absorbing at the same time, and you are asking it to do two things that directly cancel each other out. It is like asking a fishing net to catch every fish that swims through it while also letting every fish swim through freely. You cannot have both, and for most of the 21st century, nobody figured out how to get around that. Now, here is the part that changes everything about how expensive that ceiling actually was. Commercial buildings account for roughly 40% of global energy consumption, and glass curtain walls, the floor-to-ceiling window systems on modern office towers, have always been treated as pure energy liability. Heat comes in through the glass in summer. Heat escapes through the glass in winter. Every square foot of window was, by design, a place where a building lost money. Architects and engineers spent enormous budgets on double-paned glass, tinted coatings, and shading systems, all trying to make windows slightly less wasteful. None of it made windows productive. It just made them marginally less of a drain. Most people who read about solar technology never get to this part of the story because the mainstream coverage stops at rooftop panels. Rooftops are flat, sun-facing, and easy to retrofit. Vertical glass on the side of a 50-story tower is none of those things. For years, the industry simply wrote off vertical glass surfaces as unusable for energy generation, full stop. That assumption sat unquestioned in engineering textbooks and building codes alike. But here's the thing. As settled as that 1% ceiling seemed, it was not the end of the story. It was the starting line. What happened next did not come from a rooftop solar company at all. It came from a lab that had spent years chasing a problem everyone else considered closed, and the first sign of a crack in that wall was dismissed by almost everyone who heard about it. In the autumn of 2021, a group of materials scientists at a Shanghai-based solar research institute announced something the rest of the industry considered a dead end: a program aimed at building genuinely transparent, genuinely productive solar glass for commercial buildings. The stated goal was audacious: not tinted panels, not partial transparency, real, see-through glass that generated real power. The reaction from established solar manufacturers was immediate skepticism. Several major panel producers in Europe and the United States dismissed the program publicly, arguing that transparent photovoltaics had been tried, tested, and abandoned for a reason. One industry trade publication called the effort a distraction from proven rooftop technology. The consensus was that this was a research curiosity, not a commercial path. They said the same thing about LED lighting. In the 1990s, LEDs were dismissed by most of the lighting industry as too expensive, too dim, and too impractical to ever replace incandescent and fluorescent bulbs. 2 decades later, LEDs used roughly 75% less energy than the bulbs they replaced and became the global standard. We all know how that ended. The early program did not start with a finished product. It started with a stack of experimental coatings, dozens of failed prototypes, and a small test facility where researchers tried, one variable at a time, to find a material that could selectively catch light without blocking it. Most of those early attempts failed outright. A handful showed a faint, almost negligible electrical current. It was not impressive, but it was not zero either, and that distinction mattered more than anyone outside the lab realized at the time. Here is what most people get wrong about breakthroughs like this one. They assume the moment of discovery is dramatic, a single flash of insight. It rarely is. It is usually a small number that refuses to go away, buried inside months of data that everyone else would have thrown out. That small, stubborn number is exactly what kept this program alive while critics moved on to other stories. By early 2023, the skepticism outside the lab had not softened. Funding remained modest. Commercial glass manufacturers showed little interest in licensing early versions of the technology. From the outside, the program looked like exactly what critics had predicted, a slow-moving research project with no path to market. But inside the lab, something had shifted. The team had stopped trying to force a single material to do everything at once, and that single change in approach, splitting one impossible problem into two separate, solvable ones, is the detail that never makes it into the public reporting on this story. What came out of that shift was not a marginal improvement. It was the first real mechanism that made transparent solar power physically possible. Here is the problem the team had to solve first. Sunlight contains visible light, the part your eyes register as brightness and color. And it also contains near-infrared and ultraviolet light, wavelengths your eyes cannot see at all. A traditional solar cell does not care which is which. It absorbs everything it can, which is exactly why traditional panels are opaque. The team needed a material that would let visible light pass straight through untouched, while intercepting only the wavelengths the human eye never sees. Think of it like a one-way turnstile at a subway station that only lets certain people through and quietly redirects everyone else without anyone noticing the difference. Visible light walks straight through the turnstile. Near-infrared and ultraviolet light get pulled aside and put to work. The technical solution came in the form of an ultra-thin selective coating, layered directly onto the glass at the molecular level, engineered to absorb almost exclusively in the near-infrared and ultraviolet bands. The coating itself is measured in nanometers, thinner than a human hair by a factor of hundreds, and it is applied in a way that leaves the glass looking, to the naked eye, completely ordinary. The consequence of that selective absorption was the first real jump in performance. Early full prototypes, tested at the Institute's pilot facility in 2023, reached transparent solar conversion efficiencies of roughly 12%, 12 times higher than the previous ceiling most researchers had accepted as the practical limit for see-through solar materials, 12%, and the glass stayed visually clear enough to read a newspaper through from 3 feet away. This is where the mainstream coverage of solar technology usually stops, because 12% sounds modest next to a rooftop panel's 20%. But rooftop panels do not double as windows, walls, and skylights across an entire building's surface area. A building has vastly more glass than roof, and the pilot tests measured total power output across full window surfaces, not isolated cells. The verdict is simple. For the first time, a piece of ordinary-looking glass produced enough electricity to matter. But a coating that works in a controlled lab environment is not the same as a coating that survives 20 years of sun, rain, and temperature swings on the side of a skyscraper. And that is exactly the problem the team ran into next. The efficiency breakthrough was real. It was also, on its own, commercially useless, because nobody was going to reglaze a 50-story building with a material that might degrade within a few years. The mechanism that solved the efficiency problem had just created an entirely new one, and solving it required an idea that sounded at first like it should not work at all. Here is the brutal catch the team ran into after solving the efficiency problem. The selective coating that made the glass generate power was extraordinarily sensitive to manufacturing conditions. Produce it at the precision needed in a lab, and it performed beautifully. Try to scale that same process up to cover thousands of square feet of commercial glass, and the coating's performance collapsed. The cost per square foot became unworkable, and durability dropped sharply under real-world weather cycling. The apparent contradiction was this: the more precisely you controlled the coating process to protect performance, the more expensive and slower it became. And mass-market glass manufacturing depends on speed and low cost above almost everything else. Efficiency and affordability were pulling in opposite directions, exactly the way transparency and absorption had pulled apart at the very start of the program. Then came the question that changed the entire calculation. What if, Instead of applying one delicate coating layer, the glass used two layers working together. One engineered purely for energy capture, and a second, separate layer engineered purely for durability and self-cleaning, so the fragile layer never had to touch the outside world at all. It sounds like it should not work. Two layers should mean twice the cost and twice the manufacturing complexity. That is exactly why it does. The durability layer was built from a silica-based coating already used in industrial glass manufacturing, chemically bonded to sit above the energy-capturing layer like a protective skin. It sheds water, resists dust buildup, and blocks ultraviolet degradation, while letting the layer underneath do its job undisturbed. Researchers at the Institute paired this two-layer approach with a roll-to-roll deposition process, the same category of high-speed manufacturing used to produce ordinary window film, instead of the slow precision lab method used in earlier prototypes. Testing at the Institute's expanded pilot line in 2024 measured production speeds roughly 9 times faster than the original lab process, with efficiency losses of less than 1 percentage point compared to the lab-grade version. Manufacturing cost per square foot dropped by more than half. The verdict: separating the two jobs the glass had to do, generate power and survive the outside world, is what made this affordable enough to actually build. But a manufacturing process that works on a production line is still not the same as a building. Coating glass efficiently in a factory is one problem. Wiring together thousands of individual panes across a real structure, accounting for shifting sun angles, shade, and inconsistent output throughout the day, is an entirely different problem. And it is the one that determined whether this technology would ever produce a number worth certifying. Here is the coordination problem. Nobody talks about when people imagine solar glass on a real building. A single window facing east catches strong morning sun and goes nearly dark by early afternoon. A window facing west does the opposite. Windows on lower floors sit in shadow from neighboring buildings for parts of the day. Individually, each pane's output looks erratic, unpredictable, almost too inconsistent to be useful at any meaningful scale. The old approach to solar power never had to deal with this. A rooftop array faces one direction at one angle, and every panel in it behaves roughly the same way at the same time. Wire them together, and the output is predictable. Solar glass on a building's four walls behaves nothing like that. Treating thousands of individually inconsistent panes as one simple power source was never going to work. Here is what makes this genuinely extraordinary. The Institute's engineering team built a monitoring and load balancing layer that behaves almost exactly like a navigation app, rerouting traffic in real time. Just as a mapping app constantly reads live congestion and reroutes drivers through the fastest available path, the system reads live output from every individual pane, identifies which sections of the building are generating a surplus and which are underperforming in shadow, and reroutes that power internally, second by second, to wherever it is needed. This system, named the Institute's Adaptive Glass Grid, was first deployed across a 42-story commercial tower in Shanghai in late 2024, coordinating output from more than 11,000 individual glass panels, a coverage scale larger than the combined window area of most mid-sized office parks. 11,000 panels functioning not as 11,000 separate devices, but as one coordinated system. Building operators did not need to learn a new energy management platform to use it. The system integrates directly into existing building automation software already used to manage heating, cooling, and lighting, feeding live glass output data into the same dashboard facility managers already check every day. The single-sentence verdict is this: for the first time, an entire building's glass surface behaved less like a collection of windows and more like a single self-balancing power grid. But a system that performs well across one tower over a few months is not the same as a certified, independently verified result. The combined output from that first full deployment produced a number so far outside expected range that the Institute held it back from publication for an additional round of third-party verification before anyone was willing to put it in writing. Here is the honest picture. This technology does not eliminate a building's energy bill, and it is not a replacement for the broader power grid. It is a meaningful reduction layered on top of everything else a building already uses to manage energy. With that acknowledged, the certified figure itself is remarkable. In March of 2025, an independent energy efficiency laboratory verified that the 42-story pilot tower's solar glass system cut the building's net energy cost by 75%, compared to an identical, conventionally glazed tower of the same size, operating under the same conditions. 75%, confirmed by a second, unaffiliated verification team before the Institute would allow the number to be published. Translated into human-scale terms, that reduction is roughly equivalent to eliminating the annual electricity use of about 300 typical households, enough to meaningfully offset the power draw of the tower's lighting, elevators, and climate systems combined without adding a single rooftop panel. Thermal imaging captured during the verification period showed something else the Institute had not fully anticipated. Because the energy capturing layer absorbs near-infrared light before it reaches the building's interior, the tower's cooling load dropped as well, since less heat-carrying light made it through the glass in the first place. The building generated power and needed less power to stay cool at the same time. Independent monitoring estimated the tower avoided roughly 420 tons of carbon dioxide emissions in its first full year of operation, comparable to taking around 90 passenger cars off the road for a year. None of this comes without trade-offs. The upfront cost of retrofitting an existing building with this glass remains higher than standard glazing, even with manufacturing costs down by more than half. Long-term durability past the 10-year mark is still being tracked, not yet proven over decades, and the system currently performs best on buildings with significant unobstructed glass surface. A smaller structure with limited window area will see a smaller version of this result, not the same headline number. Here is the verdict the title of this video promised you. Ordinary glass, re-engineered at the molecular level, cut a real building's energy cost by 75%, and an independent lab confirmed it. If a number like that surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. Buildings consume roughly 40% of the world's total energy use, and glass surfaces represent one of the largest untapped pieces of that equation. A category of infrastructure that has existed for over a century and until now never generated a single watt of power. That is the scale of problem this technology addresses. Commercial real estate, architecture and construction firms, and grid operators managing urban demand all sit inside the sectors where this changes the underlying engineering calculus. A developer designing a new office tower now has to weigh solar glass not as a novelty add-on, but as a genuine offset against a building's lifetime energy cost. Adoption is not simple, and it should not be treated as if it were. Building codes in most countries were not written with power-generating glass in mind, which means certification and safety standards need updating before large-scale deployment can happen. Supply chains for the specialized coating materials are still limited to a small number of facilities capable of producing them at the required precision. And retrofitting existing towers, rather than building new ones from scratch, adds cost and complexity that new construction does not face. An international standards body focused on building energy performance has already opened a working review of transparent photovoltaic glazing, the first formal step toward folding this technology into recognized commercial building codes, a process that, historically, tends to take years rather than months. Here is the historical parallel worth remembering. Double-glazed windows, now standard in nearly every modern building, were dismissed as an unnecessary luxury expense when they were first introduced commercially in the mid-20th century. It took roughly 3 decades for double glazing to go from expensive novelty to mandatory building code requirement across most developed economies. The technology was never the obstacle. The adoption curve was. The genuine technical advantage here is harder to copy than a patent filing suggests. It is not just the coating formula. It is the combined manufacturing process, the 2-layer durability system, and the load balancing software working together as one pipeline. Replicating any single piece is possible. Replicating the entire integrated system at the same cost and speed is a far higher bar. The limit that held this technology back for 2 decades was never political and never about which country could build it first. It was a materials science problem, and materials science problems get solved by whoever solves them first. If turning ordinary infrastructure into a power source is the part that stuck with you, that same engineering mentality shows up again at a completely different scale, where an entire national power system was re-engineered around a similarly simple idea, and the resulting numbers are just as hard to believe. The zoom out here is bigger than one tower in Shanghai. If solar glass reaches even a fraction of the world's existing commercial building stock, the surface area available for power generation is larger than every rooftop solar installation currently in operation combined, without requiring a single new structure to be built. glass stops being a passive material that buildings are wrapped in and becomes part of the infrastructure that powers them. If you made it this far, you now understand more about how transparent, solar glass actually works than most people who write about it for a living. Here is what was actually proven. A material that physicists considered fundamentally incompatible with power generation because it had to stay transparent was re-engineered at the coating level to do both at once, manufactured cheaply enough to matter, coordinated across an entire building like a single power grid, and independently certified to cut real energy costs by 75%. If this changed how you think about what a window is actually capable of, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should power-generating glass like this become a required standard in new building codes, the way double glazing eventually did, or should adoption stay entirely market-driven and let cost and demand decide on their own? I read every single one. See you in the next one.